In the previous topic, we learned how to recognize exact equations and solve them. In this topic, I will discuss equations that are not exact, but after multiplying both sides of the equation by a integrating factor, we can turn a non-exact equation into an exact equation. So as before, we will begin with equation of the form. So as usual, we will have y prime equal to some expression in terms of x and y. But then, as before, we rewrite the equation into the differential form. So m x y dx plus n x y dy equals 0. So when we check for exactness, we want to check. So let me recall here, exact is when partial m partial y equals to partial n partial x. But in our situation, not exact. Meaning that partial m partial y is different from partial n partial x. Now in general, it may be difficult to solve the equation, but we consider the following two cases, and in each case we can find integrating factor like this. So we consider the first case is when the ratio, we compute the ratio P1 equals to partial m partial y minus partial n partial x, all of this divided by n. If this does not contain y, it does not contain y, then we can compute integrating factor mu equal to e to the integral of p1 dx. Now in this case, p1 does not have y, so it only has x, and so we can compute the integral in the variable x, and then we have an integrating factor. Case 2, in this case we consider p2, which is different from p1. It's partial n partial x minus partial m partial y divided by m, and if this does not contain x, then, well, p2 does not contain x, so it has only y, and we can compute the integrating factor mu is e to the integral of p2 dy. We need to be careful, depending on which case. Like the first case, we have integral dx, and the second case we have integral dy. After we have found the integrating factor, we multiply the equation, the non-exact equation, by mu, and then we will have an exact equation. So let's see how it works here by looking at a few examples. Example 1. We want to solve the equation. So y prime equal to a fraction like this, minus 3xy minus y squared divided by x squared plus xy. So as usual, we will rewrite y prime as dy dx. And so when we cross multiply, we try to write the equation in the differential form. We will have x squared plus xy times dy equal to, on this side we have minus 3xy minus y squared, or multiplied by dx. But then we need to move everything to one side. I'm going to move this to the left hand side, and the sign here will turn into plus. So I have 3 plus 3xy plus y squared dx plus x squared plus xy dy equals 0. I move this to that side right there. And this is our differential equation in the differential form. So then m is this, and n is x squared plus xy. Let's compute partial m, partial y. We take the derivative in the y variable. We have 3x plus 2y, and then partial n, partial x, we have 2x plus y. These two are different, right? Different. So the equation is not exact. So let's consider, let's compute P1. P1, the formula is partial m, partial y minus partial n, partial x, all divided by n. And again, you need to be very careful which terms come first and which term we have in the denominator. Let's plug in. We have 3x plus 2y in parentheses minus partial n, partial x in parentheses, which is 2x plus y here, and all divided by n, which is right here above. So x squared plus xy. We need to simplify this. Don't forget to distribute in. Simplify the numerator first. Distribute, we have 3x plus 2y minus 2x minus y, all divided by x squared plus xy. And so we have x plus y divided by x squared plus xy. At this point, we see that P1 has both x and y. But we need to simplify more in order to see what happens. So simplify. To do that, let's factor. The numerator, we cannot do anything. We cannot factor just x plus y. However, the denominator, there is a factor, the common factor of x. We take it out, we will have x plus y. And voila, we can cancel the x plus 1 here in the numerator and x plus 1 in the denominator, which give us 1 over x. So we see that no y in it. Like what case 1 is about. Case 1, P1 like that does not contain y. Now, if you compute P1 and it turns out to contain y, then you cannot continue with case 1. Instead, you have to consider case 2. Now, because P1 does not contain y, we can compute the integrating factor. The mu of x is e to the integral of 1 over x dx. So we have e to the log of, usually we have absolute value of x, but let's ignore the absolute value now when we compute the integrating factors, and we can cancel to get x. So our integrating factor is x. Now let's multiply the equation by x. Multiply through by x. Let's recall the equation is in this form, in the differential form like this. We need to multiply through by x. So x multiply here, 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 here. We get 3x squared y plus xy squared dx. And then we have x cubed plus x squared y dy equal to 0 times x is 0. Now, this is our new m. This is new n. So let's compute. Let's check that the new equation is in fact exact by computing partial m partial y. We have 3x squared plus 2xy, and then partial n partial x. The derivative in x, we have 3x squared plus 2xy. And now they're the same. So equation is exact. So you see that at the beginning the equation was not exact, but after we have found the integrating factor and multiplied the equation by integrating factor, the new equation is exact, and now we can solve the equation. Solve equation using the method that we learned in the previous topic. We need to determine the potential function, and then we have the general solution. So let me just write down the final answer here, the general solution. You may pause the video and try to solve yourself, but the equation is like this. And the solution is like this: x cubed y plus a half x squared y squared equal to c. There's no initial condition for this problem, so we don't need to solve for c. This is the solution. Now let us look at another example. We want to solve the equation y prime equal to minus y divided by 2xy plus e to the negative 2y. As before, we rewrite y prime dy dx. We get minus y divided by 2xy plus e to the minus 2y. Now cross multiply, we have 2xy plus e to the minus 2y dy equal to minus y dx. And then we move this term to the left side. The minus becomes a plus y dx plus 2xy plus e to the minus 2y dy equals 0. And now we have m is just y, and n is 2xy plus e to the minus 2y. Let's compute dm dy, just 1, and then dn dx. We have 2y, and here the second term does not have any x, so the derivative in x would be 0. The two things are different. The equation is not exact. Of course, if the equation is already exact, then we can use the method in the previous topic and determine the potential function and solve the equation, but it's not exact. So let's, as usual, let's consider two things. Consider the first P1 is partial m partial y minus partial n partial x over n. We need to check this, and if it does not have y, it has only x, then we can find integrating factor. But let's see what it is. We have 1 minus 2y divided by n. N is the whole thing here. 2xy plus e to the minus 2y. And we won't be able to simplify, right? There's nothing to factor here. So it depends on x and y as well. So we won't be able to use this. For the case 2, it should not have y. For this, it has y, so we won't be able to use. So instead, look at P2. And the formula for P2 is different. It's a partial n partial x first minus partial m partial y divided by m. And in this case, we have partial n partial x is 2y minus partial m partial y is 1 divided by m. M is y over here. So it's good because it does not contain x. does not contain x. That is case 2. If you look back, case 2 means over here, case 2, we look at the ratio of P2, and if it does not contain x, then the integrating factor is like this. But if it does contain x and y as well, then we won't be able to find integrating factor. So the integrating factor will be e to the integral of 2y minus 1 over y dy in this case. How to compute this integral? We need to split it into 2y over y, and then minus 1 over y dy. Now we have some work to do. An integral of 2y over y simplified to 2, and then minus 1 over y dy, and then we have e to the 2y minus natural log of y. Again, we ignore the absolute value. But in order to continue, we have to simplify this. We split into e to the 2y times e to the minus log of y, and as usual, this becomes e to 2y. The minus here, we need to bring it in. We have e to the log of y to the minus 1. So minus here, in fact, minus 1, and we bring in the exponent. And then now we can simplify by cancel the e and the log. So we have e to the 2y times y to the negative 1, which is y in the denominator. That's the integrating factor. Now let me recall the equation, and then we will multiply the equation through by that integrating factor. The equation is y dx plus 2xy plus e to the negative 2y dy equals 0. Now multiply through by the integrating factor e to the 2y over y. So every term here will get multiplied by that factor. So we have the first one will be, and we'll just rewrite this e 2y over y, and then we multiply by y dx. So here we have e to the 2y over y, and then 2xy, and then e 2y over y multiply e to the minus 2y dy is 0. Simplify and cancel the y to get e to the 2y dx plus cancel the y. We have 2, let's try x plus e to the 2y plus e to 2y times e to the negative 2y becomes e to the 0, which is 1. So 1 over y dy equals 0. This is our new equation. This is new m, new n. Let's check that the new equation is exact. So dm dy is 2 e to the 2y, and dn dx, take the derivative in x, and we have 2 e to the 2y. This is 1 over y, which does not have x, so derivative 0. The two things are the same, they're equal. So the equation, the new equation is exact, and we can find the integrate. We can find the potential function and solve the equation. Function psi here. You may pause the video and try yourself. But here's the details. With partial psi, partial x is the new m, right? Which is, if you go back, e to the 2y is the new m. We get e to the 2y. And then partial psi, partial y is the new n, which is from here 2x e to 2y plus 1 over y. 2x e to 2y plus 1 over y. The first one is equation 1, and then we have our equation 2 right here. As before, from equation 1, we integrate in x. We get psi equal to the integral of e to the 2y in the variable x. So let me write for del x. We keep y as a constant in this case. So we get x e to the 2y plus a constant in x, which means a function of y. And then we take the derivative in y, partial psi y, partial psi, partial y. But the derivative in y, we have 2x e to the 2y plus dh dy. And take partial derivative and equate with equation 2 with the new m. Is the equation 2 there. So we will have 2x e to the 2y plus dh dy equal to new n from the equation 2 is 2x e to 2y plus 1 over y. We see that these two things cancel out, and we get dh dy equals 1 over y. So integrating, we have an integral of 1 over y dy, and so it's going to be natural log of, let's the absolute value of y here, plus constant. But we might ignore here for now, because at the end we will have a constant. So let's plug h in. H equal to log absolute value of y into the formula for the potential function. Then we get, this is our potential function, x e to 2y plus h of y, and we have found that h of y is natural log of absolute value of y. So the potential function is x e to the 2y plus natural log absolute value of y. So now the equation, right, the differential equation as the form, the differential, total differential of psi, which is x is 2y plus natural log of absolute value of y equals 0. Which means that because the total differential is 0, we must have x is 2y plus absolute value of log of absolute value of y equal to c. And this is the general solution to the ODE. This is implicit solution. Of course, if we are given initial condition, then we can use that to determine C. Now, I want to emphasize again, the idea here is that we are given a differential equation. We rewrite the equation in the differential form like that. And we check for exact equation. If the equation is exact, then we can solve right away. But it's not exact, then we consider one of the two cases here. Okay, we consider first P1, take the ratio of P1 correctly, and check. If it does not have y, then we can compute the integrating factor, and we continue solving. But if not, then we need to look at P2, and we need to make sure that P2 does not contain x. In that case, the integrating factor is e to the integral with respect to y. Two cases are very different. So you need to be careful. If you mess them up, then you will get the wrong solution. You cannot solve it even. This is the end of the lecture.